As you all know, this series is made possible through the generous support of Dr. Lauren Trottier. McGill University is located on land which has long served as a site of meeting and exchange amongst Indigenous peoples, including the Haudenosaunee and the Anishinaabe nations. McGill honors, recognizes, and respects these nations as the traditional stewards of the lands and waters on which we meet today. So we will officially close registration tomorrow. The website's going to say that. No more registrations. So this is our team. This is our 47 officially registered for the series. You check in every week, 6 o'clock for refreshments and readings. And as you know, it finishes April 18th. You know that you can check our background readings. Someone told me they had trouble last week on the evaluation form accessing the background readings. I checked with Victor, the website manager, editor. There were some broken links, so he's fixed that. All the readings should be available, okay? The videotaping, as you know, it's Jonathan. He's our technician. He asks if we could suspend the questions with the microphone to the very end, rather than in the presentation. So we'll do that. That's the best way we can capture all your comments, your questions, and build it into a very nice webcast. Okay. So special thanks tonight to the volunteers helping us. From the Rare Books Room, Jennifer Garland and Marion. Our other members are from Missy, the McGill Sustainability Science Systems Initiative, and our moderator tonight, Heather McShane, who is the program director and catalyst-in-chief for McGill's Sustainability Systems Initiative. Heather gained a degree in plant science and a master's degree in soil science from Aberdeen University in Scotland, and then worked for 20 years as a project manager in the information technology sector. She then returned to education to study for her doctorate in environmental chemistry at McGill's MacDonald campus, and since 2016 has headed the McGill Sustainability Systems Initiative, which has one of the cutest acronyms, MSSI, Missy. Missy is building a community of sustainability researchers from across McGill, from natural sciences and engineering to humanities, management, and law, and supports research at McGill that takes an interdisciplinary, holistic, and solutions-focused approach to sustainability. Heather will now introduce our speaker.
Thank you. Right. Okay, so hello everybody. And thank you very much for the invitation to introduce Audrey. And I'm delighted to introduce Audrey because she is a co-lead in one of the McGill Sustainability Systems Initiative research themes. We have 3 research themes, and Audrey co-leads the Creating Sustainable Materials for the Future. So, Audrey completed her PhD from the École Polytechnique, France, in 2005 with the Best Thesis Award. She did her postdoctoral fellowship at Yale University in 2006, and then came to McGill, where she is now an associate professor of chemistry and a Tier 2 Canada Research Chair in green chemistry. Audrey is a leading expert in the field of catalysis using metals, metal oxide, and biomass-based nanomaterials. Her work focuses on sustainable processes and the use of earth-abundant starting materials. In 2016, her research was highlighted in Nature, and in 2017, the Royal Society of Chemistry journal Green Chemistry named her as a leading emerging leader in the field. In 2011, Audrey was awarded a Science Communication Fellowship for Green Chemistry by Environmental Health News and Advancing Green Chemistry. And in 2016, she represented Canada at IUPAC Green Chemistry Conference in Venice. So we have no doubt that she's a great communicator. She's the scientific director on the board of Green Centre Canada, which is an Ontario-based tech transfer company, and since 2017 has been the associate director of McGill's Facility for Electron Microscopy Research. And I am especially pleased to welcome Audrey because For me, as I know her, she's a successful woman scientist who manages an active and demanding career involving a lot of travel, as well as another career as a mother of a young family. And to me, she's a perfect role model for women students in science. So with that, I'd like you to welcome Audrey. Thank you.
Well, I'm really moved and touched by your kind words, Heather. Thank you so much for what you said. I mean, I actually can't remember, communicating to Ingrid, but I believe her that I did say that my title was Doing Chemistry as a Woman. So I'm going to try to rephrase a little bit and say that I think it's important to realize that more gender equity is needed in all hard sciences and chemistry in particular. So I just want to highlight a few of the role model chemists, women chemists that really led the way for us to be doing more and being bold and being curious and dare to think and to create and to discover. So I just want to spend a couple of minutes actually showing you some slides about gender equity in science. As you can see from the slide, actually, you have here computer science, where you see that there's really not a lot of women. Women are here in purple. Engineering, you're around 20 as well. And in physical sciences, you're around, 40. Around 40. And actually, it's kind of sad because in the statistics from 2004 to 2014, we actually dropped by 3%. So it's actually not very hopeful. I mean, although it's probably due to statistical error. In chemistry in particular, I think that this particular statistic is very striking to me. I think that what's really striking to me as a scientist is that when I teach large classes at the undergrad level here at McGill, I see a lot of female faces. And then as I go to teaching masters and then PhD student, those numbers drop. I mean, in my group, there's a number of students, and that's really great to have. But I see in the groups around fewer female. So I think this is really that there's something must be happening around the time of the master or the PhD where women tend to think that maybe there's other things to do in life than just have fun and do research and enjoy and be excited about discovering new things. And I think this is something to think about as we think about the gender equity in the context of hard sciences. So I like this picture where you see this woman wondering what she can do and thinking about family and money and getting married and traveling the world and all sorts of things at the same time. And I think, well, this is very much my life, actually. Except we should draw a cat here instead of the dog. But the rest is quite true. So I think rethinking about what I wanted to talk about, I like this title of saying, let's use what we have. And actually, this is kind of a female thing, right? You go home and you open the fridge and you say, let's see what we have and let's cook, right? So I guess it's the connection with doing chemistry like a woman. So I'm going to try to walk you through a few of the grand challenges around trying to make things with what the earth has to offer. And we're going to talk in particular about the abundance of resources and the abundance of energy. So I'll try to show you at the end of the lecture how in my group we're trying to use resources energy a little bit better to try to tap onto things that are more abundant or to try to be mindful of the energy that we use. So I like to think about the history of mankind, thinking about when did the revolution happen and how can we relate that to the context of sustainability. So we human beings made a number of different revolutions and key discoveries in our history. And these are often linked to techniques, in particular to chemistry. So I'll try to walk you through some of the hallmarks of that history and try to show you how chemistry was directly embedded into those particular key moments and where we are now in respect to those particular discoveries. If I take you back a very, very long way, back in prehistory, we like to call time in prehistory by calling them Stone Age or Bronze Age or Iron Age. And this is very much linked to chemistry because Stone Age is when men had to use stones that they could find. And then Bronze Age happened because men discovered how to create fire and create ovens so that they could reach temperature, so that they could start to do metallurgy. And they could start to do metallurgy with bronze, and so with copper, silver, and gold, which are easier to manage. You needed lower temperature in metallurgy to deal with those particular metals. And then, as technology evolved, then you had ovens that could go even higher temperature, and then you started to play with iron. And this is when you had the Iron Age. And of course, these different milestones were really key to the ability for men to be making tools, and to, as you went from particular gold and silver to iron, you could make many more tools because iron was a lot more abundant. I really like this book. I don't know if have some of you read this book from Yuval Harari? Yeah? Yeah, I see a few hands going up. This is a wonderful book. If you haven't read it, I really encourage you to do so. I mean, I've been given the stock for a few years now, and it used to be that people didn't know it, but now it's really in every library, so I'm not so fancy anymore talking about this. But there's a quote in there that I really like, saying, "The Stone Age should more accurately be called the Wood Age because most of the tools used by ancient hunters and gatherers are made with wood." So why did we call the Stone Age the Stone Age? Well, it's because the wood pieces of the tools that people made, they degraded, and archaeologists couldn't find that piece, but they could find the stone piece. So they called it the Stone Age. But in fact, what Yuval Noah Harari reminds us of is that in reality, during that time, lots of things were made from biomass and lots of things were made from wood. So this is why he says we should call this part the Wood Age. So at that time, we were really heavily relying on biomass. So if I think as a chemist, what I see here is a lot of carbon. So the carbon that people was using was made from biomass. And then there was another revolution that happened that really changed the way we looked into carbon. And that's the Industrial Revolution. So now we're jumping back to the 19th century. And during the 19th century, what happened there essentially is that people managed to produce massive quantities of energies by simply burning biomass, but rapidly it became obvious that there wasn't enough biomass to do that. So they turned to fossil resources. And then you have mining that took place, and this is how people have taken their resources in carbon that way. So now we can jump to today. What is the next revolution? What is new about today and how we're going to make new materials? And you could argue, well, there's new ways of making materials, so we make extra light composites for planes, or we're making extra powerful components for electronics, or we can use renewable energies or biofuel. But I would argue that the main difference between the revolution that we're living in now, the transformations that we're living now, versus the past ones, is the fact that we're conscious that we're living on a planet that has limits, that we live on a planet that is suffering from our impact and from decisions that we take. And I think that a lot of the decisions and a lot of the revolutions that are going to happen in the next decades are going to be very heavily tainted by actually this fact. So this is an opportunity, and this is also a challenge. And this is something that my colleagues, researchers, and I, and many people around the globe are really trying to tackle. So I spoke about biomass, right? And biomass is carbon, essentially. It's carbon that is going over and over in a cycle that we call the carbon cycle. And what this means is that carbon is in the air in a form of CO2. It is processed by plants here in order to become sugar, which is now sequestered in the plants. and then you can have sequester this sugar during cataclysmic events, so that they would be reduced and eventually transformed into fossil resources of carbon. Then you can burn that carbon and it could go back to CO2. And what we know of this cycle is that it's not balanced anymore. What we know is that because we take fossil resources and we burn them, we're actually changing the dynamic of this cycle. And what we do in particular is we bring scarcity to the pool of resources. So you see we have less fossil carbon. All of this is highly debated. I mean, you now have a lot of scholars who think that we're not really going to run out of fossil resources. But the second aspect is the fact that we have an excess of CO2. On this slide here, you can see that the quantity of CO2 in the atmosphere has gone up dramatically in the last few decades, and this is what is causing global warming. And finally, we also have dilution. So this is something that we don't think of, but as we release CO2 more and more in the atmosphere, CO2 is mixed with the rest of the air, so with nitrogen and oxygen, and it's present in tiny quantity. So it's present in hundreds of ppm. So it's not a lot. So the problem with this is that if we want to take this carbon back and do chemistry with it, we have a big problem because it's not very abundant, and there's other elements in the air that might react first before the CO2. So this is another thing. So scarcity on one end and potential excess and excess and dilution on the other end. So that's carbon. And what I've said here is something that you know, and you understand what I'm talking about, because this is in the news, this is in the articles, you've seen movies and TV shows about it, so I'm not talking about any new thing to you. So we spoke about carbon, but I'm a chemist. And as a chemist, I need to do something in my slides. I need to have a periodic table, right? This is what we chemists do. We put periodic tables everywhere. Actually, you'd be amazed. At the American Chemical Society, this is a society where they want people to subscribe and give money for the society, like any society, right? And in order to have them bring a new friend, they give them a present. And they say, if you bring a friend to the American Chemical Society, we'll give you a present. And the present is a throw that has the periodic table on it. And of course, every chemist is like, oh, I have to get my throw. So, which I realize is something very odd about us chemists. So what I'm trying to say here is that behind carbon that you understand well, you have to imagine that for each and every of the elements that you see here, you're going to have to face the same problem. For instance, if I take, I don't know, what can I take? I can take silver here. I'll talk about silver later in my talk, but silver here is used a lot for a number of applications, for jewelry, but also in a lot of chemical processes and a lot of transformations. And because we use it for a lot of things, people think that we might run out of it in a few decades. Another one that's interesting is zinc. So where is my friend zinc? Zinc is an element that we use a lot for making paints to galvanize metals, so that we can make poles that don't rust, essentially. And zinc is actually something that used in really, really large quantity, and people think that we might run out of this element at some point soon, and we'll be in trouble to replace it. So zinc is over here. So this is to give you an example that some elements are what we call endangered, like endangered species. And chemists talk about this and reflect upon how to use alternatives and develop alternatives to those metals, so that if we are to run out of them, we could potentially continue with doing what we do. So here is my question for you. All the things that you have around you, the painting on the wall, this cement that is making this building very sturdy, the chairs here, all of the things around you are made from chemicals that we can produce. So those chemicals, they may come from biomass. You remember the nice huts that we saw from the past? They are made of biomass. But But we also use mined materials. We use a lot of petrochemicals in order to make, this chair is made of a lot of petrochemicals, almost entirely, actually. So what do you think is the most sustainable? Would you say it's the biomass, or would you say it's the mined materials that are most sustainable? I heard a few things. Biomass is better? Yeah, biomass is better, but then, I don't know. Because if you use rocks, or if you use sand, sorry, yeah. So mined materials, if you use rocks, okay.
I think it's saying it's closing. It does
Oh.
it every time.
Okay.
But not for us.
Oh, not for us. Okay, good. So if you use stones, for instance, for making things, it actually might be very sustainable. And if you use biomass, but in order to plant the plants that you need for your chemicals, you actually kill a lot of forests, maybe this is not sustainable. So actually, I would argue that biomass is not necessarily that great. I mean, it depends. It could be a fantastic idea if it's a waste, if it doesn't compete with food, if it doesn't compete for arable land. So there's a lot of conditions that you need to think of. And mined materials is the same story. If you're depleting resources, if you're causing imbalance, such as the CO2 excess, then it's not good. But if you use perfectly abundant materials, and we'll talk about iron in a minute, iron is very abundant, it's non-toxic, it's a great element to use. And it's mined, but that's okay. So in fact, from biomass and mined materials, you can make everything that you have around you. And the question that sustainability has to address is how can we continue to do that without losing opportunity, without creating major pollution, and with sustained resources. So making sure that we use things that we can reproduce and that are going to be sustainable over the long term. So who has one of these? Everyone? Yeah. So how many, you remember the periodic table I showed you, right? How many elements do you think there is in this? 50? I heard 50. More? More? Actually, it's not bad, 50. It's actually 46. So this is an older version of the iPhone, so maybe now it's changed. Maybe it's a few more, I don't know. But that's this quote is amazing. So 80% of all the production of platinum group metals, indium, gallium, and rare elements took place since 1980. So if you think of all the usage of the precious metals, indium, gallium, and rare earth elements, 80% of the mankind usage happened over the last 40 years of the whole mankind history. This is amazing. We're using those resources like crazy. And this is really difficult because some of them, they're not so abundant, and you may run out of them. I mean, for instance, in iPhones, you do have gold, for instance, and it's quite expensive. And, the mining conditions of gold are also a question. You have arsenic in your iPhone. Did you know that? This is incredible. You have cadmium, gallium, phosphorus, strontium, molybdenum. You have crazy elements. You have, where is indium? Indium is here. Indium is extra important. Indium is this element that is making your touchscreen touchable. So it's going to make your touchscreen so that you have a contact, you have electricity going through, and it knows then where your finger is. And indium is really massively mined, and we have a problem with this resource. We don't know if we're going to be able to sustain that much longer. Lithium is another similar element as well, where we have questions over long-term sustainability. So global mine production of base metals increased by a quarter over the period of 5 years between 2006 and 2011. So another periodic table, love them. What is key to understand is that the reason why we use all of these specific elements is that we have, especially over the last hundreds of years, explored and analyzed the chemistry and the properties of each of these elements, and we figured out what they are the best at doing. And what we did is we composed the perfect team, like you're a soccer team coach, and you're trying to assemble the perfect team for doing what you want. You need the guy that goes super fast with the ball, so that and you need the guy that stays here but super rapid to catch the ball, and you need, I don't know, I'm not a soccer person, but and the idea is the same here. So with your periodic table, you're going to pick the element that are going to be really good at giving an electron, taking an electron, capturing light, and then you also have the combination of those elements. And by all the research that's taken place, we've really optimized that, and now we're using them for the best. But the problem is that if we start to have a lack of resources for some of them, then we're stuck because we don't know how to make the products so performant. So there's really is a question around this. So I'm talking a lot about some metals that are scarce and some metals that are abundant, and this is kind of capturing that. So I showed you the periodic table as a nice table. Now what you see here is the same periodic table. As you go from here to there, you go down the periodic table, essentially. And what you see here is the abundance. So here you see the metals that are essentially at the top of the table. They're very abundant. They're the metals that you find in rocks. But as you go down the periodic table, you start to hit precious metals like silver, ruthenium, rhodium, palladium, osmium, iridium, platinum, gold. And those are rare. You don't have a lot of them. You see the abundances several orders of magnitude lower. So these could be metals where you could have problems of supplies. And of course, I've spoken a lot about supplies and things that maybe you've not heard a lot of, but all of these concepts have to be linked as well with the bigger picture. Making, producing gold, for instance, results in a lot of poverty in the countries and a lot of abuses in the countries where this is happening. So you have social issues. This is actually people who are revolting because they want to become independent from Morocco. This is in the Sahara region, and they have major resources in phosphorus, and Morocco doesn't want to get rid of this. So there's a lot of upheaval in this region for this reason. This is a place in Ghana where a huge proportion of the electronic waste goes to be recycled, and people suffer terrible conditions in order to recycle them. And also you have, of course, environmental issues. This is a process to make aluminum, which turned really bad in this little Hungarian village in the year 2012, where essentially a very basic, a very toxic sludge completely flooded a village. So this is really horrible. And also the question of economics. So we cannot talk about scarcity without saying that it's going to have a consequence on the price. So I mentioned indium, this little element that is so key for the screen of your phone. It's, of course, guess what? Its price is going up really crazily. So I think that with this, we can think of a number of ways as researchers to look into how we could change things and improve things. And there's several things that are kind of the take-home message for me as a researcher. One is that we can try to use better biomass, but of course being careful to not have competition with food and to try to understand better how to generate fuels from them. And there's a lot of challenges around biorefinery, so going from oil refinery to biomass refinery, and a lot of people are working really hard in this area. You also have the ability to try to help by making greener processes. So this is more what we do in my group. So for instance, if you look at the United States of America and you look at all the energy used in industry across all industries, a quarter of this is just for chemicals. And if you add petroleum refining, it's actually more than half of the energy. So there's a lot of potential here to diminish how much humanity consumes if we can make processes much cleaner. We're also trying to do things with less waste and trying to use, again, metals that can be abundant so that we can recycle, so that we don't have resources issues. And finally, also trying to tackle the problem of pollution and toxicity. And this is something that we're doing, amongst other things, with Heather in the framework of MSSI, where we're trying to make materials benign by design and try to think, okay, this thing is going to be pollutant, this thing is going to be toxic. Can we try to change the elements, change the composition, and have the same function without the toxicity? So this is some research that we're doing, but as you imagine, it's very challenging and it requires a lot of collaborations with a lot of people. So we're fortunate at McGill to have really good people to do that and amazing colleagues. So hopefully in the near future, I'll be able to present some of that to you as well. But for today, I'm going to talk a little bit about chemistry and processes. So I'll try to make that easy, but you'll have to bear with me for a second. So there's a process in industry called hydrogenation. Hydrogenation is the process by which you add hydrogen to your molecule, dihydrogen in this case, so 2 atoms of hydrogen. It's a molecule that has 2 atoms linked together, and you want to add them to a molecule. Typically, you can take oil, and in oil you have a functionality in oil that can be hydrogenated. And when you do so, you tend to turn oil into a solid material. And people, when they figured this out, they said, oh, great, we're going to make oil that we can spread on butter. And this is how they invented margarine. So the way this is made industrially is that you take oil and you stir it with water in the presence of hydrogen gas, so this H2 gas, and in the presence of nickel. And nickel, the role of nickel here is going to help break the H2 bond and plug the H2 onto the molecule. The same process is also applicable to the synthesis of Advil. So you all know Advil. It's a drug, and in order to make this drug, you need 6 steps. And one of the steps is the same hydrogenation reaction. And for this, you need to use palladium. So this is a metal that is less abundant than nickel, and there are questions around using it. One question is the price of palladium. So we mentioned its availability, but it's linked to its price. So you see palladium here and platinum have a price that varies a lot and that is quite high compared to, for instance, nickel or iron that I'm going to talk about in a moment. But it has other consequences as well. Palladium is toxic, and if you make a drug and you have palladium in it, that's not good. So regulation bodies in European Union and the US and Health Canada, they've all set up some goals so that you don't have too much of these metals because it would be damaging for you. You don't want to have a pill and then take toxic metals. So what companies do is they use very long columns that are embedded through this big cylinder. And in this column, there are things that are going to trap all the metals. But this is really expensive for companies to do. So there would be a lot of benefit for companies to try to work with metals that are non-toxic inherently. So what we decided to do was to use magnetic nanoparticles of iron. So the advantage of magnetic nanoparticles is that we can recycle them magnetically. So we can take a little magnet and take them out. The advantage of iron is that it's cheaper and non-toxic compared to palladium. So we wanted to study them, and we studied them in the context of the hydrogenation reaction. But there's one major issue with iron, is that it rusts, right? You all know that. Iron rusts, so it forms, this is iron, right? And when we try to use them in processes, we use them as very, very tiny pieces of iron, so they're nanoparticles, and they also rust. There's no they see water or they see oxygen and they rust. And what this means for them is that they grow a little shell of oxide around them. And what this means is that you cannot use it in catalysis. Well, it's not completely true. Actually, in civil engineering department here, Subesis Koshal, my colleague, is using iron in order to depollute aquifers that are polluted by these really nasty chlorinated solvents. What you can do is iron 0 here is going to break this bond here and gradually remove the bad chlorine that is in these molecules. And he does actually use this particular guy, iron 0, with the shell of oxide. So we started to think maybe the shell is not a problem. Maybe the shell is porous. Maybe we can still use it. So We were inspired by work from another country. So this is really something that happens all the time in research. You have colleagues that discover things, and then you say, oh, that gives me an idea. I'm going to do it. So there are people in Holland that discovered that small particles of iron 0 can do this hydrogenation reaction. So you see H2, you plug it onto this position, and then it makes this molecule that you want to have. But the problem is that their particles were very small, and as soon as this saw water, they completely shut down. So we figured by using our iron 0 nanoparticles with the shell of oxide, so they're here, they're all aggregated together because they're magnetic. And now we can do this transformation here. So we add H2 to this, and it works very well. And we can do this with H2 and iron 0, which is really interesting. Now we can do this even in the presence of water, and it works. We can recycle it with a little magnet, and the iron oxide shell, instead of preventing activity, actually protects the iron 0 that is vital for this process. We also developed, with some partners in Japan, some refined system where we can put the iron 0 inside a column within a polymer. And now we can do this transformation in almost in 90% water, so almost pure water. And this reaction works very well and doesn't need any precious or toxic metal. And at last, I want to talk to you about another project, and actually the person who did a part of this research is actually in this room, so it's even better. What we decided to do was to see, so what I've been talking about right now is the idea that we could use non-precious metals to do things that precious metals do. The second thing that we're trying to do is to say, can we do the same process, but now use less energy to do the process? So to drop the requirement in heat, or as we're going to see here, in pressure that we need to impart to the reaction conditions. So on this slide, what you see, it's a drawing, but it's representing what is happening in reality. You see cubes of, this time the metal is silver. And the reason why we pick silver is that silver has very specific properties. Silver can be exposed to light, and the silver is going to have optical properties. So it's going to absorb the light and give energy to electrons inside the metal so that it can be a lot more reactive. So it transforms light into chemical energy. So it's very similar to photosynthesis in a way. Photosynthesis, plants take light and then turn it into chemical energy. So particles of a number of metals, including silver, gold, or copper, give extremely colorful materials, such as this cup here that is blue or green, and this is because it contains alloys of gold and silver nanoparticles. The stained glass in the Middle Ages, the red color is made of gold that is embedded inside the glass, and this is why you have such wonderful colors that never really faded over the centuries. So if you ever go to a church and you see a real ancient stained glass, you can think of the red color being little pieces of gold in it. And it's coming from a property, so I won't go into the details, but it's coming from a property that electrons inside the particles are oscillating, and the way they oscillate means that they can absorb the energy. And they do this, and they give this energy to electrons. So they give this energy to electrons. They also can give this energy and form heat, or they can also give this energy and have an intense field. But for today, I'm really going to talk about this one, where they take the energy and they transfer it to electrons. And this is how we do our chemistry. And then this electron we transfer to molecules, and this is how we do our chemistry. So this is where we got our inspiration. You see those cubes here? So this is the cubes of silver. And those cubes of silver, they can absorb light, and then they will have intense excitement at the tips of the cube. So you see here, what you see here is intense electromagnetic excitement. And this is where you have the maximum of this effect of the electrons being fed with high energy, essentially. And in that case, they were using it for an oxidation reaction. But you remember I'm interested in hydrogenation, right? So at that time, one of my students, Alain, was working on using silver to make this process here. We do hydrogenation, but only of this position here. We don't want to touch these other ones here, and that's very difficult to do. But silver knows how to do it. Unfortunately, one issue with silver is that it requires really harsh pressure. So 40 bars here, it's like going like 40 meters down on the sea in terms of pressure that you need. So you need a really harsh pressure of H2, and this takes energy to do. You need to compress pumps, and it's really demanding in energy. These molecules here are really interesting because they have applications to the perfume industry. So what we did is we made the cubes. So these are actually images that Alex here took, where she made those cubes. You see they look very cute. They're all over the place. Most of them are cubes, so this is remarkable. I mean, it's a fantastic synthesis when you think of it. You can control the fact of making all these cubes. They're very similar sizes, and occasionally you'll have an odd guy like this one here or this one there, but most of them are really nice cube. And they absorb in the visible region. So what this means is that I send light, and this position is going to be strongly absorbed. This is the property that I've been talking of. And then what we did is we made this experiment. So remember, I want to hydrogenate this position here. And when I have 1 atmosphere of H2, so this time it's ambient pressure. So we use a little balloon to do it. When I don't have any light, I have no activity, as you can see here on the screen. But if I shine light with a simple light bulb, now suddenly I transform my molecule. This is really cool. I take my H2, I split it, and I plug it where I need it. And I only do this at 1 atmosphere. It's very difficult to do with silver. And finally, if I have a laser that I concentrate only where I have the slight excitation, I'm going to have the best result. And this means we can start to work with that. So we also measured that the more light we send, the more we can transform our molecule, and this is really cool as well. So I won't go into the details, but essentially we tested it on a bunch of molecules. This is what we like to do. When it works once, we like to showcase and do it on multiple molecules so that we can tell people, hey, we can do it on X number of molecules. And then people are like, yeah, cool, I can do it on more, and you know. But essentially the idea is that you can still work with 1 atmosphere, and it works fairly well. And we can do, you remember this molecule? I said it's very important for the perfume industry. This smells a bit like flour. It smells really strongly. And we can make now this guy with a really good yield under 1 atmosphere, and no one can do this. So this is really cool. And I'm not going to go into the detail, but that's another thing that we scientists like to do. We try to understand what's happening. So we explain all the steps. You see your H2 molecule here. You see how I split it, and I plug it onto my silver, and this is how the chemistry works. And we can have, with the light, something very different than when we just heat. And this is where it's interesting, because we discover new ways to access our processes. So I've been showing you that, and we did another transformation, but I won't go too much into the details. And now I want to tell you that with all these works that we're doing, I've showed you a number of things that we do in our lab, but we don't work just together. We also have a team of people, and we're trying to have these big centers. So this is a center around green chemistry. What's unique at McGill is that we work with chemistry, but we also work with people in management or with people in engineering, so that we start working together. And this is really remarkable because it's not so usual in academia that people work across disciplines. And mind you, making management student talk to chemistry student, this is not, but it works. And when you see this working, it's really, really impressive. And now we're taking this to the next phase. So these are centers that are now a little bit older, but the new thing that we're doing now is to go even further. So now we're going to add pharmacologists, toxicologists, eco-scientists, natural resources scientists. And with Neil Basu and George Demopoulos, I'm really privileged to be co-leading the sustainable materials theme within MSSI. So MISSI, as you called it. Yeah, McGill Sustainable Systems Initiative. So we're working really hard to assemble the team and the competencies, and I hope to be able to talk to you about that in the near future. I mentioned a few of my students as I walk forward, and this is really important. None of what I described was done by me. I owe my students gratitude and the really remarkable individuals and young people. They're really creative and super hardworking, and this is thanks to them that I could show you some of the research that we do. And I want to thank in particular Alex Gillet, who's in the audience over there. We also have to thank funding, because this is how we get to be able to buy our chemicals and our machines. So this is the few people that I've been working with in order to do that. And finally, I want to spend like really 2 minutes, I think this is what I have, just talking a little bit about women in chemistry and what we're doing at McGill to improve a little bit the gender bias. So I couldn't really talk about women in chemistry without talking about my grandma, who's unfortunately passed away now. My grandma was really a wonderful inspiration for me. She never went to university. She never did any studies, but she was an incredibly curious woman. And she would stop everywhere she was and just try to observe what was around her and try to understand her to the best, to understand what she had around her with the best of her ability. She dreamt to be an associate to an explorer. So her vision was that she would follow a scientist somewhere and just take his notebook and write down everything that he did and everything that he said. And she was very humble as a human being, so she never dared to be the scientist herself. I think she had the quality for that, but she never dared thinking about that. But she wanted to at least be close to science, which I've always found really quite nice. And one day, she actually found a baby bat in her window pane, and it was abandoned, and she took care of it for a few days, and then eventually it passed, and she didn't know why. So she took her knife and she opened her stomach, and she realized, she said, oh, the lungs are full with milk. So that's how the bat died. And then she stuffed it with cotton, and she kept it for some time. So she was that kind of a woman, and she really was an inspiration to me to pursue studies in science. What I want to say is that at McGill, we really, this is a real photo. At McGill, we really think about women in academia, and there's a number of initiatives on campus. I mean, there was a wonderful event today that was organized around the question of women in ESTM and talking to young students, and it was lovely to see that. One of the things that I participated in is one initiative that was led by MAUT around women in science, or women in academia in general, and family care in particular. So I've been chairing some committees around childcare within MAUT. So MAUT is essentially the association of professors and librarians. We had a survey in 2014 on childcare access for faculty member, and I won't show you all the details, but essentially the immense majority of participants felt that McGill should be doing a better job at helping childcare on campus and solutions around there. So this is something that we've been having as a take-home message, and we've worked towards this. And actually, more recently, we actually signed a partnership with a private childcare called Kids and Company, so that we would have privileged access to their facility through MAUT. So this is one of the things that we're working on. Also in 2015, I was named the chair of the Joint Board Senate Subcommittee on Family Care, which is something that was created from a PGSS initiative. And this is really a nice setup where we're trying to take the whole spectrum of family care situations and try to help gather information about this. So what we've been doing is helping MAUT, fund a partnership with Kids and Company. We created a website, and actually I realize now that I don't have I didn't put the address, but you can ask me for it. It's just www.mcgill.ca/familycare in one word, and you'll find all the resources around childcare, elder care, healthcare, schooling, and also a number of other resources. And right now we're working on policies for pregnant students working in the lab and accommodation for students with academic duties. So I've been working on this with a number of people, with Petra Horbach and Ian Butler at MAUT, but also the subcommittee on family care has involved a bunch of people, so I'm very grateful to them, and their excellent work in this area. We're really working really hard to help this move forward, and we have a lot of exciting opportunities in this area in the future years. And I would like to thank you. Well, I would like to thank Heather and Ingrid and all the staff and also people with the technique. It's really important, and all the volunteers. And I would like to thank you very much for your attention tonight.
So, if you wondered whether women can do chemistry, wonder no more. You've just listened to some really cutting-edge science there. So thank you very much, Audrey. That was absolutely fabulous. And thank you for the rest of the stuff that you're doing as well to make sure that women can come in and don't have to choose between motherhood and having a career in science. It is possible to do it both.
Absolutely.
So we now have, 10 minutes, and we only have 10 minutes because last time, apparently, we were so excited. By last week, we ran over, and people had to stay, and they didn't want to stay. So we have to. I'm going to cut you all off in 10 minutes at 7:30 to give the final thanks. But before that, we have 10 minutes to ask Audrey some questions. We don't have written questions, so there are some volunteers here who I believe are going to hand around the microphone. I would ask you to speak. Yeah. Okay, but
No,
I just want to tell you that you'll need to use the microphone because of the AV. So that when you get it, the AV will be available in May. When you get that, so yes, hold on to that thought. When you get that, you will only hear questions that have come through the microphone. So although I know we don't really need to use it for us, we think of our future generations who are still going to be listening to us. So I'm going to give you this microphone.
I just want to say it was very nice seeing you again because you were with us last year, were you
Yeah,
not?
it's true. Yeah.
And I just remember you very fondly. It was very well done again.
Thank you so much. I added some new stuff, so because I figured that maybe you guys
Were
would.
you not in Chile with the group last time? The Atacama?
No, I wasn't in Chile. No, I don't think so.
I don't.
Okay. Yeah.
Okay, thank you.
Thank you very much.
Okay. So other questions?
Can I just ask, perhaps, do you think your trajectory would have been different? Your career would have been different if you'd been a man?
Yeah, so would my career be different if I'd been a man? I don't know. I have no idea. It's really hard to answer that question, actually. I'm not sure what it is to be a man, you know? So I observe them, but
I'm just thinking about
Yeah.
perhaps your grad work, the experience as being a grad student. Would that have been different, do you think? Or did you have a cohort
I
of
don't
women
know.
that you were with? Or
I don't know. I don't really know. I think, when people say that the variability between women and between men is not greater than the variability between a man and a woman that you take arbitrarily, I think it's true. I mean, I see men being extremely narrow-minded and focused, and I see men being extra, doing a lot of different things, and I see women doing a bunch of things and others being more narrow. I mean, there's many different ways to practice research, and I think that I don't really see a pattern here. I'm not sure that maybe in other sciences, maybe in social sciences, it's a bit different. I don't know. But in science, I really have the feeling that we're really trying to base things on facts and results, and we're trying to be objective about it. And I don't think that's because we do science differently that they would be barriers. It's rather because of other reasons, potentially like self-confidence, and also reasons linked to extracurriculum activities, essentially having a family and so on. Yeah. So I can't answer your question, unfortunately. I don't know. But maybe, can I ask you a question? Would your life be different if you were a man?
Mine?
Yeah.
Yeah, I think it might have had a different trajectory in terms of,
Okay.
who I talked to, who I worked with. I think it might well have gone in a different direction. Yeah.
Interesting. I I don't think I can say the same about me, but I'm not sure how general that could be. Yeah, but thanks for sharing.
Other questions? I have a question. I'd like to follow up from your question, because I think my trajectory would have been different if I had been a man. But I would like to ask you were inspired by your grandmother, and I heard from Ingrid last week that you were inspired by Marie Curie. Is that true?
Yeah, I mean, it's difficult, being raised in France to avoid the kind of like inspiration from Marie Curie if you do any sciences. And so one of the reasons why I thought of her as a child is because I used to do all my homework on the floor, like. And my mom hated that. She felt it was like horrible. And she said, because apparently Marie Curie did the same thing to work on the floor. And I don't know where she read this or heard this, and she kept saying it, oh, you're like Marie Curie, you work on the floor, it's terrible. You scientists, So yeah, I don't know. That's kind of this is the connection I have with her. Yeah.
Do you see yourself as an inspiration to young women? Do you specifically reach out to the young women in your undergraduate and especially your master's degree programs where you say that this is where you think women are falling off? Do you reach out to them to nurture their interest in any way?
It's a difficult question. I'm not sure how people see me. I think I'm a little bit crazy and I do really too many things. And I'm not sure how much it's not scaring people sometimes as well. But I don't know. I am trying to play my part and going to do outreach, and I really value this idea that the role model is important. It certainly was for me. I mean, through someone who wasn't really a scientist, but someone who was cultivating curiosity, and it really inspired me from a young age. So I think that I value that, and I want to do my part in this. So this is why, today I did some activity with with Mary Rose over there. It was really wonderful. And I'm doing outreach, and I've been doing, women in science at Dawson, and I love doing that. It's fascinating. But what impact does it really have? I think it's difficult to quantify and to measure. So I wouldn't have the, I can't really say how much an influence it is. I think what you have to do is you have to play your part. You have to do it. You have to do your share. And trust that maybe you'll see the grain somewhere. Actually, I went with actually the outreach group of McGill a couple of years ago to the classroom of my daughter, and one of her friends, I see her regularly, and since then she says, "I want to be a chemist. I want to be a chemist." So I don't know if this would be the closest thing I have to a proof that maybe I have inspired someone once in my life, but yeah. She's 8, so I don't know if it's going to last much longer.
And I think that some of the people who were here last week will remember this false modesty. No, not false modesty, female modesty.
Yeah, no.
Where a man might have just went, yeah, I'm a great role model. Okay, you can cut that out. There we go.
Thank you very much. I was really interested in the fact that you went back and looked at some of the early women chemists that, and a little bit of the history. But then when you began with the prehistory, I'm an anthropologist, so I'm ready to give you a little bit of a hard time on that.
Yeah,
because the slides that you have showed only men inventing things. In the industrial revolutions or the various revolutions, we can go back to them and take a look.
It's very
I know
true,
that's
possibly.
the material that you can pick up because you can't make all those slides yourself, but and even when you talk about the wood revolution, we often forget there must have been fiber revolutions where women, most likely, made all of these, all the clothing that people wear. We're naked. We don't have fur all over us. And there's a reason, because we've been producing our own clothing forever and they protect us. But we don't have a record of that either. Just as wood disintegrates, textiles do. So here, we don't have anything with the Stone Age, then you can go to the Wood Age. But what about the fibers? And what about clay? And
so you're right. Actually, I give this kind of talk in many different formats, and I have another slide where I talk as well about animal-based biomass, and on this I have pictures of natives, and I have a lot of women on those ones because, you know, we're talking more about clothing and so on. So it's my fault. I should have kept that one, but it's a very good point. I should think about that more. I mean, I have one, you know, with silk, amongst other things. And
Right,
you see
or cotton,
and
or-
you see,
or
cotton, and you see the
hemp, or-
women processing silk. So I think it's just a little bit because of I was trying to condense things and I removed slides quickly.
It's not even this one. I think it was the
No,
earlier
it's this one
Go
here.
back.
So-
This one, and
Yeah.
the textile revolution had women in textile factories, but you can go
It's
to the
true.
one before this too, which is even there.
one
There we
here,
go.
yeah.
There we go.
So
They're all
you're
men.
right. I mean, I was trying to find, if you have a better image, I'm more than happy to change that one. I just browsed through Google and tried to find
Sure.
an image to have the Stone, Bronze, and Iron Age. But yeah, I'd love to have more women on this one for sure.
Right. This is the kind of thing that in, you know, museums we've been trying to change for decades.
You know,
to
I mean-
change the image of women in museums so that they're not always seated on the floor doing something like holding the baby and the men are all standing up doing some activity. And it's just so unconscious that people don't recognize they're being taught something about gender roles as they see it. Here, I'll give you this.
No, absolutely. And I apologize, I had slides when there was more women. But if you have a better alternative to this, I mean, I'm going to leave you my card. I mean, please do send it to me. I'd love to change that to make it better. Absolutely.
Great. Do we have one last question? Okay, so with that, I would like to thank Audrey very much.
Thank you so much.
Provide you with the official gift.
Thank you so much. Thank you. Thank you very much.
Okay. Next week is March 28th. You have Natalia Gomez from the Department of Earth and Planetary Sciences will be talking on Earth and Climate Science and Women at McGill. And don't forget there are background readings should you wish to look at them. Thank you very much.